In this video, we're going to look at infrared spectrographs, how they are created, and the features of the graphs that allow us to determine the functional groups that are present in the molecule. If you find this video helpful, don't forget to share, like, and subscribe, and look out for new videos. Infrared spectroscopy. What happens on infrared spectroscopy? Well, the first thing we do is we take a sample and we put it in an infrared spectrometer. Now, an infrared spectrometer actually is a machine that produces different frequencies of light rays in the infrared region. That's the region of electromagnetic radiation that is just to the other side of red light. That's why it's called infrared. And we take different frequencies and we pass them through the sample. So we start off with one frequency, we pass it through the sample. As it goes through the sample, some of it is absorbed and some of it is transmitted. The transmitted light is then, what it does is it is detected by the detector. Now what actually happens in the sample is we pass the light through the sample, the bonds of the atoms absorb the energy and they start stretching when they absorb the energy. Now that stretching motion, or that stretching backwards and forwards, it's called a stretch, is the atom has absorbed the energy of the light, and because it did that, less light is passed through to the other side. So we're going to see that we're going to see bits of energy that are missing, and we call these peaks stretches. They're caused by the stretching. Some of them are caused by bending, and you can think about the bending like a mass or stretching like a mass on a string. So the bonds of different functional groups will absorb different colors of the infrared spectra. Now infrared spectra have colors like we think of as Roy G. Biv or the visual light colors, but there are different frequencies of infrared light, and different frequencies of these, or different wavelengths, because we measure these plots and wavelengths and per centimeter, actually absorb different functional groups absorb different wavelengths. So let's have a look at this graph and see how we unpack this. So just before we start, we've got a whole bunch of bonds here. So these are the different types of bonds between atoms. And remember that what I said is that if the infrared light hits these bonds at a certain wavelength or certain frequency, the range here is wavelengths. So if the carbon-hydrogen bond is hit by an infrared light that has a wavelength of 3,100 to 2,800 per centimeter, okay, then what we're going to get is we're going to get that energy absorbed, and it's going to be absorbed because, remember, the bonds will start stretching and they'll use that energy to make their vibrations or their resonance happen. The alcohol bonds, that's OH bonds attached to a carbon, is going to absorb it in the 3,300 to 3,700 range. The carboxylic acids, this 3,600 to 2,500, which what we call a broad peak. Okay, so it's going to absorb energy in that range. The amine will have a double peak in the 3,500 to 3,100 range. Now, when I talk about these ranges, they'll become apparent when we look at the next graphs. Okay, any peaks that we get below 1,500, which is and that usually happens not from the stretching of these bonds, but they come about from the kind of bending of the molecules or the bending of the bonds. Now the bending of the bonds, actually the patterns of the types of bonds, so the bending that happen in different molecules are not consistent, so we can't actually use the bending peaks to identify the type of bond, but we can use this region as a fingerprint. So what we mean is that anything below the 1,500 region is going to be the same for any molecule we test. Let's have a look at some of these graphs and see if we can understand what I'm talking about. So here we can see a CH stretch. Now a CH stretch happens here between 2,800 and 3,100. See here that this indicated blue section here, this peak Well, it's actually an absence of the light coming through. So it's like a big deep trough, but we call it a peak where you imagine it upside down. This peak, sharp peak we call it, comes about from the carbon-hydrogen bonds stretching. And remember, they sucked that energy out of the light to make themselves move. And now when the light is measured, it's not there anymore. If I go below 1500, I can see some peaks, but those peaks don't mean anything. Okay, so the peaks are used for fingerprinting. That is, we can take a look at this peak and it will tell us exactly what the molecule is. But if we have an unknown molecule, we know it's got CH bonds because we see the CH stretch between 2800 and 3100 per centimeter. Okay, let's have a look at the next one. So an OH stretch. So we can see on the left here, this is an OH stretch. So if we see a large trough, or this sort of generally shaped, triangular shaped trough here, between 3,300, 3,700 centimeters per centimeter, we have an alcohol group attached to a carbon. We can see to the right here, we actually have the CH bonds as well. Often the CH stretches are present in most molecules because most molecules have hydrogens bonded to carbons. So this one here is a really good OH stretch for a carboxylic acid. Notice that this is very, very broad. We know that this is also a carboxylic acid because we see also another CO stretch, C double bond O stretch associated with the carboxylic acid. So we've got this very broad peak between 2,500 and 3,600. That's for the OH stretch. If the OH is attached to the carbon, also has a carbon double bond oxygen. So that influences how it stretches, right? Because it's bonded to this carbon with a double bond oxygen. So therefore it's got this bigger range that it's going to absorb the energy. Also notice that this peak here, the C double bond oxygen peak is present. Well, if this is a carboxylic acid, then that definitely will be present because a carboxylic acid has an OH and a C double bond O. Notice we can see on the bottom of here as well a wee peak, sharp bits pushing through. This is actually the CH stretch. We can see it at the bottom here. So we've got this broad part that comes about from the oxygen to hydrogen bond, but we can also see it's the overshadowed part of the carbon to hydrogen stretch that's just poking through the bottom here. Okay, so again, here's the carbon to oxygen stretch, double bond oxygen stretch. It's quite clear. It's in the middle of the graph here. This has the peak between 1600 and 1850. Here we can see it's at 1800. And it's very definitive for a C double bond O stretch. On the left here, we can see that there is a carbon-hydrogen bonds in this molecule because there is this peak here. This indicates a carbon-hydrogen stretch. And see all of this bit here on the right-hand side, below 1500. Whatever this molecule is here, now it's unknown at the moment, but if I actually had a picture that looked exactly like this and I knew what that molecule was that I had the picture for, I could use that to identify this because this is called the fingerprint region. It will have the same peaks for any given molecule. It's just, I can't say which peak originates from which functional group, but it will have this fingerprint for any molecule below 1500. Okay, and that is, oh wait, let's, okay, so sometimes we see a nitrogen to hydrogen stretch. Often it will be seen in an amine, not an amide. For an amine, we will see this double peak. Okay, so the double peak just to the left of the CH peak. And it's in a specific range between 3,100 and 3,500. We won't see this if there is an alcohol present because the alcohol will mask it, or if there's a carboxylic acid present. But if it's just an amine, we might see this double peak. Sometimes it's quite small, but we can use it as supporting evidence if we've already noted on our mass spectrometry mass spectra graph, that there is an odd number for our molar mass, then the peak here on the IR graph is often used in conjunction with that for us to identify that the molecule does have an amine functional group. More. Here we go. So this is going to look at the C to carbon double bond to carbon stretch. Now look, this is really, there's usually a peak about here between 1500 and 1650, but when I say usually there isn't always a peak, and sometimes there is a peak just above 3000. So if you see this C to H peak here, but then just on the side you see this little bit, it might indicate a carbon to carbon stretch. This is a bit finicky, it doesn't always turn up, it's hard to see. I often don't rely on these IR graphs to identify carbon to carbon stretches, especially because we know that we have these carbon 13 NMR graphs that actually clearly indicate when there's a carbon to carbon double bond. There's not a lot of information that can be garnered or gained from these IR graphs to tell us about the carbon to carbon stretch, carbon to carbon double bond stretch, because often they're really hard to identify. So don't be afraid not to use these. And look, this is all the different groups that we need to know for IR spectra. Use this IR information, this infrared graph information, in also with carbon 13 NMR graphs and mass spectroscopy graphs for unknown molecules, and you should be able to determine what the actual molecule is. I'm going to put up some videos that go through exactly how you might do this, and hopefully you can get onto those and they will help you as well. Okay, if you've got to this part of the video, you've obviously watched all the examples that I had on those 3 questions. Hopefully this has fortified your understanding of geometric isomers, and you are now well prepared to go and attack that exam. Good luck, and if you found this video useful, don't forget to like it, subscribe, and look out for new videos that I might put up by clicking that bell. See you later.